Time for a pop quiz. Succente final GPT-10. Easy as pie.
There it is. I knew someone would get it. Hi everyone, welcome on in. My name is Penn Center. We are here today for some linear algebra. We're just waiting for some of those pre-roll ads to roll on through, and that way we won't get stopped midway through the presentation. Clonade is here with us today to deliver an amazing presentation on basis and dimension. Let's get that fired through. How are you doing, Anders? Hope you're doing well.
Hardly even a practice test.
We'll get that fired through, and then I'm going to turn the bot off just so that we don't get distracted as we work away on some linear algebra today. Oh, I see. That's weird. Chat is behind me. Chat. I need you up here, chat. There we go. Okay, we're going to pop over into Discord, so if you need to and you want to join along via Discord, you can get into the simple server through our server here. Oh, damn, right, the bot's not working. Shit, okay. So you'll have to go, just kind of click on through down below the video, and then you'll be able to get a Discord link through there. And if you get into the Element server, I can direct you over to the simple server if you want to view the lesson in Discord. Otherwise, we're going to be redirecting that lesson here onto Twitch. I just will, for the most part, be off mic to let Clonade have the floor to speak, and Clonade's going to be introducing us to basis and dimension. So let's head over there and say hello. Hello, everyone. I hope you're all Doing very well today. We have a very special guest, Clonade, who is going to come in and present to us on basis and dimension. So this is our meeting number 3 for the Friedberg Linear Algebra reading group. And I'm going to pass the floor over to Clonade to get this party started. So we will be redirecting this onto Twitch. So if you have any questions, you can post them into the Discord chat or onto the Twitch chat, and I'll do my best to kind of help moderate that discussion. And without further ado, I'll let Clonade jump on in.
All right, well, thank you for the introduction, Ben. As he said, I will be presenting bases and dimension relating to vector spaces. It is one of the most important lessons in linear algebra, at least of chapter 1, to be specific. And yeah, so I think that it's first best if we go into a kind of recap. So last time it was Cluster who presented, I believe, and he went over some definitions and theorems which should prove useful to be reminded of, to be able to understand these lessons. So let's start with a definition. Let's start with nomenclature. For the rest of this lecture, I will be denoting V as for any vector space, and S will denote a subset of V. This is so that I don't have to write out that V is a vector space and S is a subset every single time. So just keep that in mind. Then we have our first definition. For some vector V in V, it is a linear combination of vectors in S if there exists an infinite number of vectors u1 through un and scalars a1 through an such that V is a sum of the multiplications of the scalars and the vectors. Then from that we get another definition. If S is not equal to the empty set, then the span of S is the set of all linear combinations of vectors in S. And for convenience, we defined the span of the empty set to be the set containing the zero vector. Then we get on to our first theorem that Cluster presented, and that is theorem 1.5. So let the span of S be a subspace of V. Or rather, the span of S is a subspace of V if S is a subset of V. Moreover, for a subspace W of V, if S is contained in W, then the span of S is contained in W. It is useful to note that the span of any set is in itself a vector space. That will be useful to keep in mind for later. As for why this theorem is true, to give a quick overview, if you have S entirely contained in W, and W is by definition closed under addition and multiplication, by definition, any possible linear combination of vectors in S will be included in W. Then we have another definition, and that is just some nomenclature, and that is that S generates or spans V if the span of S equals V. I forgot to make it sans serif, but okay. And we finally have two more theorems to go through, theorem 1.6 and theorem 1.7. The theorem 1.6 essentially says that if a subset is linearly dependent, then the set is linearly dependent, which makes sense as adding more vectors to a linearly dependent set can't change the fact that one of the vectors can be described in terms of others. And the corollary of that theorem is that if we have these be a subset of S, then if S is linearly independent, then T is also linearly independent. That will also be useful later. Finally, we have theorem 1.7. If S is linearly independent and V is in V, but V is not in S, then the union of S with V is linearly dependent if and only if V is in the span of S. That might be a mouthful, but it essentially says that if V is a linear combination of other vectors, that is, that if V is in span of S, then if you add that vector to S, then it's going to become linearly dependent because it is, by definition, a combination of other vectors in S. And yeah, that. Are there any questions thus far? Anything I should mention to recap from last lesson? Okay, well, then we may continue. So, basis and dimension. First, let's define what a basis is. A basis for a vector space V is a linearly independent subset of V that spans V. That is just the basic requirement and the only requirements for a subset to be a basis. So let's put that in the corner. Then we have some examples. So, for example, since we have that the empty set, the span of the empty set is equal to the set containing the zero vector, the empty set is linearly independent by definition, at least in the book. The authors decided that for a set to be linearly dependent, it must be non-empty. So the empty set is linearly independent, and the span of the empty set is the zero vector space. Therefore, the empty set is a basis for the zero vector space. Then we have the set of all n tuples of length 3. So if this is a basic example where if we have, well, first we can see that this is linearly independent because there is no way to express one in terms of the others. But also we can easily show that this set spans F3 because if we have A100 plus B010 plus C001, that is equal to A, B, C. So you can express any element in F3 with 3 scalars. So effectively, the free tuple of A, B, and C is enough to express any single element. Then we have the same logic for matrices. One thing that's important to mention, when we have n tuples like this, specifically where each, for any finite set of finite n tuple set, if we have a set of n tuples where each n tuple contains 1 in a unique position, this is called the standard basis. So this is the standard basis. Then we have the same argument for matrices. And yes, the set spans the set of 3 tuples. If we can combine elements like where each matrix holds 1 in a unique position to effectively get A, B, C, D, and therefore this set spans the all 2x2 matrices. and it's linearly independent. Then we have an example of polynomials. You can combine polynomials of 1x, x squared, x cubed, x to the fourth, and so on, to get a standard basis for Pn. But it is worth noting that we can also have infinite bases. So for example, if we have P over f, so the set of all of infinitely long polynomials, we have an infinitely long basis, because you cannot describe a you can always find a polynomial greater than the last power of x in a finite basis. So it's good to keep in mind that bases can in fact be infinite. That being said, the author decided to not define what it means for an infinite set to be linearly independent, so that can be discussed. But for now, it's fine to just accept that bases can be infinite. Oh, wrong one. So let's get our first theorem out of the way. Theorem 1.8. Let beta be the set of n vectors that is a subset of V. And then beta is the basis for V if and only if for every V in V, we can write to V as a unique linear combination from vectors in beta. That is, that V can be described as a1u1 plus a2u2 up to an with unique scalars a1 through an. Let's just rewrite that in a more concise form and put it up there as well. Let's follow through with the proof for this. Let beta be a basis for V. And then we have that span of beta is V by definition, and that implies that for all V in V, V is also in the span of beta. We are currently proving that if beta is a basis, then each V can be expressed as a unique linear combination. We'll prove the converse after this statement. So if you take two vectors, I probably should have named, if you take, well, not two vectors, let's suppose that you can actually express a vector in two different ways using the assumptions stated above. Well, if you write those two vectors out and you give them different scalars, you can subtract one from the other to get that 0 equals m1 minus b1 u1 plus a2 minus b2 times u2, and so on. So we just subtracted the two equations, and since beta is linearly independent, we know that the only solution for this equation is where all of the scalars are 0. Therefore, a1 minus b1 is equal to a2 minus b2, and so on, is all equal to 0. And it follows from there that a1 must be equal to b1, a2 must be equal to b2, and so on. So let's now prove the converse. Let beta be a vector of n, a set of n vectors, that's a subset of V. Then, if for all V in V, you can write V as a unique linear combination with vectors from beta, show that beta is a basis. Well, this proof is more simple than the other ones, or than the other, because if we have unique scalars, that means that 0 must be expressed in a unique way. So that, and we know that if we must express 0 in one and only one way, the scalars must all be 0. One question that may arise from this is, what if we have, for example, u1 and u2 be your u2 be the additive inverse of u1? Couldn't we just subtract u2 from u1? Well, if we try that, and let's say that we are working with vectors of one tuples, why not? So let's write u1 as a one tuple of 1 and u2 as a one tuple of -1. And so then we can let a1 equal to a2 equal to 1, because we will subtract 1 from 1 and get 0, right? But, well, what if I choose a2 and a1 and a2 to be -1? Because if we multiply both by -1, we will just get the opposite of both, so they will essentially switch places, right? So therefore, since we have two different ways of describing the zero vector, that breaks the unique scalars requirement. So that shows that the only way to write 0 is by using all zeros. Contradiction, yeah. Yeah, so usually you would show this via contradiction by essentially assuming that beta is not the basis, and then proving that some statement contradicts that the beta is not the basis. But this is honestly the best I could come up with, because the book gives the converse as an exercise. And also, it's worth noting that 0 cannot be in beta, because if we have unique scalars and 0 is in beta, you can write 0 as 0 times any vector. Therefore, it would also break the uniqueness. So it follows that beta is linearly independent. And since beta is linearly independent and beta spans V, well, we haven't proven that beta spans V, but it shows that if for every V in V, we can describe V as a linear combination of vectors from beta, that beta spans V. And from those two statements, we can conclude that beta is in fact a basis. So I think before moving on to theorem 1.9, it would be good to show an example. So to quickly grab one from the book, we have that, for example, take the set to be, take some subset to be 2 minus 3, 5. So of 3 tuples, 2 minus 3, 5. Then we have 8 minus 12, 20. Minus 12, 20. Then we have 1, 0 minus 2. And we have 7, 2, and 0. Oh yeah, my bad. There should be a comma. 8 minus 12. Thank you for pointing it out. So, let's assume that, well, not assume, but it can be shown via methods described in the last lecture that that S does in fact generate R3. So we're working with n tuples over the real number, 3 tuples over the real numbers. So we can select the basis by using, well, actually, this is an example for theorem 1.9. So I'm just quickly gonna take this, move it down, and I'm just gonna select. If I can actually select, that would be nice. And then move it down. Right over there. So, actually, I should show you the entire thing on screen so that I can select it later. So, right. We have theorem 1.9. If S is a finite set, a subset of V, and it spans V, then some subset of S is a basis for V. This essentially means that we can reduce a subset of V into a basis. So if we write that into a more concise form and place it up there, we can go on to the proof. So first we take the simple examples. If S is the empty set or if S is the zero space, we get that the vector space it's a subset of is also the zero vector space, and the empty set is a basis. Well, why is that? Because the span of both the empty set and the zero space is in fact the zero space, one by definition and one by just realizing that when any way you add the zero vector is going to result in the zero vector itself. And so that takes the simple case out of the way. So let's move on to the other, well, for the rest of the sets. So we first choose beta to have one vector from S, which we call U1. Beta will be, by construction, a linearly independent set. The reason why we can pick one vector out of S is because the set consisting of one non-zero vector is always linearly independent. There is no way to express zero in terms of a non-zero vector except via the trivial representation, that being 0 times u1. And so we will choose other vectors u2 through uk such that beta stays linearly independent, and that by adjoining any u from S that is not in beta, it becomes linearly dependent. So essentially, we will construct a beta such that it contains as many possible vectors from S such that it doesn't become linearly dependent. We move it out of the side, and this is kind of in the way right now, but so I'm just going to quickly move this. So we have I can actually move this to the other screen. Okay, good. So we have let's V be a vector in S. If V is in beta, then we have used it in the construction of beta, and V is also in the span of beta, because we can just do 1 times the vector to get itself. So essentially every non-zero vector, every vector actually is a linear combination of itself. So, but what if V is not in beta? Then we have that by definition of how we constructed beta, we have that beta union V is linearly dependent. And using theorem 1.7, which says that if we have not this, but this, right? Which says that if we have a set is, if we have a set S, which by unioning some vector V becomes linearly dependent, then that mutually implies that V is in the span of S. That is what the theorem described in the last lecture states. And with that, we can conclude that V is always, in fact, in the span of beta. So, since V is in the span of beta, we can conclude that S is also contained in the span of beta. Why is that? Well, if we choose any vector in S, it will be in the span. So all vectors of S will effectively be contained in the span of beta. And by theorem 1.5, we get that since S is in the span of beta, and because span of S is in fact equal to V, we get that span of beta is equal to V, or essentially that beta spans V. Vector theorem 1.5 states that if we have a subspace W of V, if S is contained in W, then span of S is contained in W. That is theorem 1.5. So we use that theorem to essentially conclude that the span of beta is in fact equal to V, or rather that beta generates or spans V. So since beta is a linearly independent subset by definition, by how we constructed it, and since it spans V, we conclude that beta is in fact a basis for V. So now we can come back to our example. Well, this is, yeah. Now we can come back to our example, where if I just take the text, I just take the text, if program will let me select it, there we go, and then I move it over here. So we have this set of 3 tuples. So the way, what theorem 1.9 essentially says, as I said in the beginning, is it lets us reduce this subset of V into a basis. How do we do that? Well, we select some non-zero vector in S. So for example, let's pick the first one, 2, -3, 5. So our basis beta is gonna contain 2, 3, 5. Then we check if any of the vectors currently in beta, if by adding any other vector for the next vector we would select, if that would make it linearly dependent. Notice that this vector is 4 times the next. If we multiply it by 4, we get 8 minus 12, 20. Therefore, we will not include 8 minus 12, 20 in our basis set, because that would make it linearly dependent. So we go to the next vector. Next vector being 1, 0, minus 2. Since we cannot describe 1, 0, minus 2 with any combination of, with any multiple of 2 minus 3, 5, we can safely add it to our basis vector, basis set. And finally, we have 7, 2, 0, which we also cannot describe using any combination of these two vectors, so we can also add it to our basis set. And as such, we can, for example, see that not only if we actually go through each of the vectors and try to make them equal 0, we'll actually see that the only way to do that is by using the trivial representation. Because we have constructed this set to be linearly independent, and we can also show that this set spans V by essentially doing the well, not row operations, that's for linear combinations and independence, but essentially we get that if we can show that this set spans V, we can show that beta is in fact a basis. Well, thing is, one thing I forgot to mention, S is by definition a set that spans V. So essentially what we did is we took out the vectors that make it linearly dependent, and yeah, so essentially what we did by using this method is we took a set that generates V and we took out all of the redundant vectors out of it. And by doing that, we have constructed our basis. So that essentially covers an example of theorem 1.9 and how it works. And now, without many examples, with just theorem 1.8 and 1.9, we can move on to theorem 1.10. If I can find my mouse real quick. Oh, right. My mouse has disappeared, which is not the best thing in the world, but I should be able to yeah, so there we go. If I just do this and then this to delete it, there we go. So let's move on to theorem 10. It is quite lengthy, so let's take it step by step. Let G be a subset of V containing n vectors that generates V. So we have a specifically sized set containing exactly n vectors that spans V. Let L then to be a linearly independent subset of V containing exactly m vectors. G doesn't have to be linearly dependent or linearly independent, but L has to be linearly independent. If we have two such sets, or rather subsets of V, then M will always be less than or equal to N, and there exists some subset H of G, so of the subset that spans V, there exists some subset containing exactly N minus M vectors, such that the union between the linearly independent set and the our subset of G generates V. And yes, this is called the replacement theorem. We will see why a bit later. So as usual, let's make it more. Let's make it shorter to make it fit on the screen nicer. It is quite a mouthful of symbols, but let's move on to the proof. So we have, this is going to be a proof by induction. Hopefully everyone here is familiar with induction. But just in case anyone isn't, it basically, the short version of it is that we prove some base case to be true, and then we prove that from one case we can prove the next. And it's like a chain of dominoes falling on each other. Instead of, if you had some dominoes stacked one in front of another, instead of having to push each one down one by one, aka proving each case separately, which may be impossible if you have infinitely many cases, you put them in such a way that proving one will prove the next, which will prove the next, which will prove the next. That is, in short, what proof by induction is. So we have our base case where M, the number of vectors in a linearly independent subset of V, is 0. In this case, we have that L is the empty set because M is 0, so the number of vectors is 0, and we can take H, the subset of G, to be equal to G, and so unioning the empty set with H will just give H, and since H is equal to G, H spans G. H spans V, my bad. So that concludes the base case, and that is the simple part. And then we have the inductive step, m plus 1. So let L be a subset of V with vectors from 1 to m plus 1. So it contains m plus 1 vectors, and let it be a linearly independent set. Since L is linearly independent, we have, by the corollary of theorem 1.6, that a subset of L is also linearly independent. So we have that the vectors from 1 to m is also linearly independent. And because of that, the induction hypothesis, that being our hypothesis that m plus 1, that m proves m plus 1, can conclude that m is less than or equal to n, and that there exists some h that contains n minus m vectors, that is a subset of G, such that the span of the vectors v1 through vm union h, or rather u1 through un minus m, that spans V. This is quite a lengthy and relatively complicated proof. So if there are any questions, I'll do my best to answer them once we complete the proof. So we have that there exists some scalars a1 through am and the b1 through bn minus m in the field of that the vector space is over. such that the linear combination of A1 V1 through AM VM and B1 through B1 U1 through Bn minus M UN minus M is equal to Vm plus 1. This essentially means that we can describe the last vector in L, the m plus 1th vector. Yeah, sure, I can put it like that. It's kind of weird English, but sure. So we can construct the last vector in L by using a subset of L and using the remaining amount of vectors missing to substitute, or not substitute, but to complete the set. Note that in this case, n minus m must be greater than 1. Otherwise, Vm plus 1 would be a linear combination of just V1 through Vm, contradicting the assumption that L is linearly independent. So essentially we have that n is greater than or equal to m plus 1. So thus we have that n is greater than m, which implies that not only is n greater than or equal to m plus 1, but also that some bi, or rather bi, is not 0 for some i. So that means that not only is n greater than or equal to m, but one of the terms containing a vector from U must be non-zero. So we then solve for U1. We can solve for pretty much any vector in the sequence, but let's just solve for U1. We have that the U1 is equal to, well, since we have to divide by b, so we get b minus 1, b1 to the negative first power, and we also have to multiply by negative 1 because we subtracted by u1, b1 u1. So we essentially multiply. Exactly. As Ben said in the chat, we can solve for one of the vectors because we know that one of them is not 0. We can solve for any single one of those u vectors. And we get this linear combination. Now notice, what I wanted to notice is I should have removed the top equation and slid the bottom onto the top, but I didn't quite have the time to finish this, so I ended up doing it like this. But if you remember about approximately what the linear combination looked like, and you let H be U2 through UN minus M, because we are solving for U1, then it's shown that U1 is in fact a span of L and H. L being the containing the vectors V1 through Vm, and H containing the vectors U2 through UN minus M. And we have shown that since U1 is a linear combination of those two, that U1 is in fact in the span of the union between L and H. And from there, it follows that V1 through Vm and U1 from U to UN minus M is contained as well in the span of L and H. We get those V1 through Vm and U2 through UN minus M by the fact that any vectors contained in a set is also contained in the span of said set. So we essentially know that v1 through vm and u2 through un minus m are contained in the span of L union H. And we have also shown that u1 is also contained in there. And so since we know that the span of L union H spans V, we also know, well, rather, we know that the set of V1 through Vm and U1 from U to Un minus M spans V. So therefore the span of L union H is also V. Let me just make sure I got that right. Thank you. It took a while to. It took more time than I expected to construct these animations, but I managed to get there in the end. Oh yeah, one thing I should note is that I didn't quite have the time to encapsulate everything in today's lecture into Manum. Into these animations. So I will continue once we finish with the proof of theorem 10, and once I answer any questions some might have about it, I will continue by writing things out and using the book as reference. So we have essentially shown that L union H spans V. And so finally, since H is a subset of G, and we have constructed an L, we have constructed an L that, if I go back a bit, we have constructed an L such that L contains m plus 1 vectors, right here. And we have an H, which is from U to from UN minus M. Let me just note that. I accidentally exited VLC. That is just amazing. Let me just pull that back up. I accidentally went too far and the video ended. So since H is a subset of G, and since the length of H, so the amount of vectors in H is n minus m minus 1, because we didn't contain U1 in H, but we have shown that H union L spans V. We have shown that H contains n minus m plus 1 vectors. So essentially, we have shown that if we have for some m to be true, we can prove that the m plus 1 case is also true. And since m plus 1 is true, we can show that m plus 2 is true, and so on and so forth. Essentially, we can prove this for any m. So essentially that wraps up the animations that I made for this lecture. I will take note how that for my next lecture I will provide myself a sufficient amount of time to create one that can last the whole lecture. But we have now proven the replacement theorem. It was a little thorny, so to say, but we got there in the end. The theorem 10 is called the replacement theorem because we can show that essentially the way we prove this is by replacing by having a set that generates V and some by complementing some other subset, complementing a subset of the set that generates V with some vectors such that the union of those two also generates V. Oh, that essentially is where my animations end. So I will continue by drawing in Excalibur. Now we have a few corollaries. So my pen, okay. Let me just see the drawing touch. Okay, so we have corollary 1. Also, I will close. I will quickly close the ink so that it doesn't provide input lag. Right. So we have the corollaries of this replacement theorem are probably the most important statements in the entire first chapter of this book. So we have corollary 1. So let V be a vector space having a finite basis. So if we have a let beta be a basis for V, a finite, let beta be a finite basis for V, then we have, if I remember correctly, that every basis for V, that every basis for V has the same amount of vectors, the same number of vectors in it. Every basis for V and has the same length. So this essentially tells us that the number of vectors in a basis for a vector space is an intrinsic property, of the vector space, or rather of the basis. The proof for this is so if I go down here and write proof, so suppose that beta is a finite basis. Beta is a finite basis for V. Then suppose that we have another basis for V, which we'll call gamma. So suppose gamma is any other basis for V. Then we need to show that the length of B, that length of beta, my bad, is equal to the length of gamma. So how do we show that? Oh yeah, right. Let me just zoom out a bit. Yeah, so I'll be scrolling down as I write so that I don't run out of space. Yeah, so we need to show that the length of beta is the length of gamma. We show that by showing that gamma is a subset of beta and that beta is a subset of gamma. Essentially shows that that they're equal. So let's say that the length of gamma is n plus 1 or some n. So let's say that beta is n long, that it has n vectors, and that gamma has n plus 1 vectors. Then we have that by replacement theorem, which I probably should have kept on the screen. But then we have that the replacement theorem essentially says that since rather not that gamma, my bad, not that gamma contains the n plus 1, but let's say that some subset S contains n plus 1, contains n plus 1 vectors. So we have by replacement theorem that that since beta generates V and gamma generates V, that n plus 1, we have that since we have a subset of gamma that has n plus 1 vectors, we have that n plus 1 is less than or equal to n, which is just
It looks like we might have lost Clonade there, so we'll hang out for a few minutes and see if he comes back to us from the other side. Are you still here?
yeah, I am.
Oh, excellent. Okay, something went funky with your microphone. So you were talking about this contradiction that happens, and then all of a sudden your microphone went a little crazy.
Oh, did it? Is it fine now?
I can hear it now. Can you just say something else for me?
Sure. So what I'm trying to say is that fine?
Yeah, that's good. I just wanted to make sure that it was still porting through to Twitch, so everything looks like it's.
Okay, my bad. I'm not sure what happened, but sorry to anyone who is listening.
So you may just want to just go over that last statement that you gave one more time.
Yeah, so essentially I have arbitrarily chosen for S to be a subset of gamma, right? I can do the same thing with beta. So I can essentially say that S, the length of S is n plus 1 for an S that is a subset of beta, and we also get that n plus 1 is not, in fact, less than or equal to n. So we must say that beta, the length of beta, is some m such that m is less than or equal to n, right? So essentially, because of that, I could have used other variables, but if we have that, or I should have used m plus 1. Yeah, so let's do m plus 1. M plus 1 is as in uh, oh, did my screen capture go? Yeah, okay, my screen capture did a funny. Let me re-enable it. Okay, that should work now. Yeah, so essentially you can reverse the roles of beta and gamma, and we obtain that, so beta must be some n, where n is less than or equal to m. Therefore, we have that n is equal to m, and that implies that the length of beta is equal to the length of gamma. So this is essentially showing that that every basis has the same number of vectors. And that allows us to go into a very useful definition, or maybe not so much useful as important. It'll be useful later. So let's scroll down and let's construct a not that and what I just wrote definition. So a vector space is called finite dimensional. So it's called finite dimensional, that is the term. If it has a basis consisting of a finite amount of vectors. So if a, or I'm going to write it as if bases of V contain a finite amount of vectors. So essentially, the property of bases, that is their length, the amount of vectors inside of them, is called the dimension. So let's write that down as another definition. The number of vectors in the bases of V is called its dimension. So if we have a basis, if vector space has a basis that contains 3 vectors, like in our previous example of the example showing theorem 1.9, then the dimension of the vector space is 3. And we denote that by denoted by dim v. So by dimension v, by dim v, we denote the dimension of v, and any vector space that is not finite dimensional is of course infinite dimensional. So essentially, it's the same with linear dependence and independence. If a set is not linearly dependent, then it's linearly independent. In the same way, if a vector space is not finite dimensional, it's infinite dimensional. That is, that the basis contains an infinite number of vectors, like in this, like with polynomials that I mentioned earlier in the first examples. But so let's go through some examples. So the dimension of the zero vector space is 0. Why? Because the basis of the zero vector space is the empty set, and the empty set doesn't contain any vectors. Therefore, the dimension of the zero space is 0. Then we have Fn. So we have the dimension of any vector space that is an n-tuple vector space has dimension n. Why? Well, by the previous example of F3, where we had the standard basis of 1, 0, 0, 0, 1, 0, and 0, 0, 1, we can see that it has 3 vectors, and that so if we have an n-tuple, we have n vectors in the basis. The dimension of let's say m of n times, let's say n times m, or I should say m times n, not n times m. So of matrices with dimensions n times f over the field f is mn. Because for the standard basis, we have to allocate each unique position a 1, and therefore we have n times n positions, so therefore we have the dimensions being m times n. Then we have let's say, polynomials. So we have the dimension of some finite polynomials is equal to n plus 1. Why plus 1? Well, because let's say that we have a constant. This is a 0 polynomial, polynomial of degree 0. So this polynomial essentially has one basis, or one vector in its basis, that is a constant. If we have x, so if we have x plus 1, then we need 2 vectors. We need x and 1 to construct a standard base. So to construct a standard basis for x to the n, we need x to the n minus 1, and so on until x to the first power, but we also need x to the 0th power, which is equal to 1. So that's why we need n plus, that's why the dimension of the finite polynomials is n plus 1. And of course, the dimension, we don't have a dimension of p other than infinity itself, but this is, as far as I know, not really used. The dimension is noted when we have a finite vector space. So I'm just gonna put a question mark above it. Right, so those are some examples of the amount of dimensions. Then we have actually, so I would like to construct 2 more examples, and those are going to show that the field that you're working with can in fact affect the dimension of the vector space. So the vector space of complex numbers that is over the field of complex numbers has dimension 1. So if we have the dimension of the vector space V over the complex numbers, that is equal to 1, that being if V is the vector space of is, let me just write it out, is the vector space of complex numbers. Complex numbers. But if we have the dimension of V over the real numbers, then that is 2. Let me just add that the basis is then the set containing 1. Because the scalars can also be complex numbers. But in this case, the scalars cannot be complex numbers, they can be real numbers. So this also applies, and the basis is then the set 1i. So the field that you have your vector space over can sometimes affect the number of dimensions it has. And then we essentially have that we come to corollary 2. So if I just go up, not that, if I just go up and zoom out a bit. So I can just line this up. Corollary 2. Corollary 2 consists of 3 different parts, actually. It consists of A, B, and C, at least in the book. Corollary A says that if we have a subset of a vector space, let's call it, let's call it G. So if we have G is a subset of V such that span of G equals V and that the length of G equals N. So essentially saying that if we have a generating set for the vector space V that is of length N, or let's say at least N vectors, then, so let's say n plus c for some, again with this, for some c in the natural numbers. So if we have that G that spans V and it has at least n vectors, then we have that subset of G that contains exactly n vectors is a basis. Or rather, yeah, we can say that if we have a subset of G H, if we have H that's a subset of G, where the length of H is n, implies that H is a basis for V. Yeah, so if I zoom out a bit, but so that is still visible. So we have that if we have this statement essentially. So it's what essentially it is saying is that since that any basis must contain at least n vectors, where n is the length of some set that generates V. Then we have the second part of the corollary, and that is that any linearly independent subset that contains exactly n vectors is also a basis. So let's write that down too. So if we have, again with this, I keep writing lines. So if we have some linearly independent subset, let's call it S, that is a subset of V, then we have if length of S is equal to n, described above, then that implies that S is a basis. And finally, oh yeah, I should probably read chat just in case. But okay, so we have the final part. So this essentially says that that a linearly independent subset of G has exactly n vectors and is a basis. And it also any linearly independent subset of V can be extended to a basis. Or B. So what we have shown in theorem 1.9 is that any subset of V that generates V can be reduced to a basis. And what we have shown with theorem 1.10 is that any linearly independent subset of V can be extended to a basis. So that is useful to know. And that so do we have already been here for an hour and a half. Should I go into the proofs for this corollary, or should I continue with the material and the next theorem so that I can hopefully talk a bit about infinite vector spaces, or rather vector spaces with infinite dimensions?
That's totally up to you. It depends what you would rather do, I guess. So if you want to do maybe an example and then jump into the infinitely dimensional spaces, that's cool with me.
Yeah, okay, I think I'll do that then. So proving these can then be left as an exercise of the viewer. Gotta love saying that. It shouldn't be too difficult. The proofs are relatively short, and so yeah. Essentially, the book provides a bunch of examples which say that, which don't, honestly, to me, they aren't very good examples because they just say corollary A proves this is a basis. Corollary 2B proves this is a basis. So I don't think the examples, most examples in the book are quite helpful in this scenario. But I think it would be good to just talk about the overview of this entire lesson, or rather this chapter. So essentially, we have theorem 1.9, which talks about the relationship among linearly independent subsets and bases, as well as generating sets. And so we have also shown from here that if we have a Venn diagram, of linearly independent sets, and if we have some spanning, I should probably write that a bit to the left. If we have linearly independent sets and spanning sets, that the combination of the two is a basis. So that is just a good way of visualizing it. And essentially, if we have a finite basis, then all of the bases for the vector space that has a finite basis contains the same amount of vectors, the same number of vectors rather, and that number is called the dimension of V. And so essentially, that is the main point we are taking away from this lesson, because the dimensions are an important concept that will come in later in the book. We'll talk about vector spaces with with different dimensions and whatnot, but that comes later. But okay, so one last theorem is contained in the book, and so that theorem essentially states that if we have a vector space, or rather, if we have a subspace W, so let's say that let W be a finitely No. Let W be a finitely dimensional subspace of V. Then we have, or rather, no, right, I wrote it wrong. No, let W be a subspace of a finitely dimensional subspace V, or vector space V. So sorry, my bad. I wrote it wrong. That is completely on me. Let W let W be a subspace of a finitely dimensional vector space V. Then we have not only that W is then finitely dimensional, but also and the dimension of W is less than or equal to dimension of V. Less than or equal to dimension of V. So if I zoom out a bit, let's see. We have that to be perfectly honest, I didn't go over the proof of theorem 1.11. Oh yeah, I should probably specify that this is theorem 1.11. So apparently I didn't adequately prepare myself for this lesson, and I am sorry about that. So again, I think I'm forced to either read out from the book verbatim, which I don't think is the best use of our time, or I can just say that to read the book as reference, or even try proving it on your own if you are up for a challenge. But that essentially covers the lesson of bases and dimensions that concerns specifically finitely dimensional vector spaces. Most of the book will talk about finitely dimensional vector spaces instead of infinite dimensional vector spaces, as far as I know, at least. So it's worth noting that unless otherwise noted, a vector space is finitely dimensional. That being said, I would like to talk just a tad bit about infinite dimensional vector spaces and something about what's known as maximal linearly independent subsets. So essentially, I want to show more or less that every vector space has a basis, whether it's infinite dimensional or infinite dimensional. Thing is, though, just to warn that the way that this is proved is uses something known as the axiom of choice. And the axiom of choice is non-constructive, meaning that just because we proved that that the basis exists doesn't mean it tells us how to construct said basis. So that is essentially in general, the axiom of choice is a hot topic in mathematics. But talking too much about the axiom of choice and Zorn's lemma and whatnot would delve too deep into set theory, which is not the topic that relates much to linear algebra, or at least it doesn't relate to what we are talking about in the book. So I don't think it's worthwhile to talk about set theory right now. But feel free to discuss it during other times, because it is a discussion worth having. It's definitely a discussion worth having, but I don't think it's very useful for people trying to learn linear algebra. So essentially, let's start with a definition. So let f, I'm going to denote the like a fancy f, but well, I should probably say let at the beginning of it. Let f be a family of sets. A family of sets is just a collection of sets, so nested sets. That is a set containing sets inside of it. So then we have that a member of F is called maximal with respect to inclusion if M is contained in no member of F other than M itself. So what does that actually mean? That means that M is called maximal if it's contained in no other member. So to provide an example, if we have the set that contains a set containing 1, another set containing 1 and 2, and the set containing 1, 2, and 3, then 1, 2, 3 is maximal. Because 1 and 2 is contained within 1, 1, 2, 3. And 1 is contained in 1 and 1, 2 and 1, 2, 3. So 1, 2, 3 is called maximal here. There can be multiple maximal members. If I put 4, 5, 6 at the end here, that would also be a maximal member because it's contained nowhere other than by itself. So that is what maximal means. So to skip over to what the book calls the maximal principle. I will not call it the principle, but for simplicity, I'll call it an axiom. So maximal axiom. The reason for this is that it doesn't really, if you were to research what the statement actually means, it's basically a collection. So it's basically Zorn lemma, but but relating to partially ordered sets by inclusion. So what that means is, again, outside of the scope of this lecture, but the maximal axiom essentially states that, again, let F be a family of sets, be a family of sets. And if for each chain, for each chain C that is in F, there exists a member in F such that M contains each member of C, then F contains a maximal member. So what does this mean? Well, first I need to define what a chain is. A chain is essentially a collection of sets where for each pair of sets A and B in C, either A is a subset of B or a B is a subset of A. So if I didn't do that, I didn't draw a line. This, for example, this is a chain. Why? Because you can pick any pair of two sets within this outer set, and one will be a subset of another. So if I picked 4, 5, 6, that wouldn't be a chain anymore, because I can pick some other set like 1, and show that neither is a subset of each other. So that is what a chain is. And what this actually says, if you have some chain in F, so if, for example, this entire set up here was in F, and we have some other chains, M contains each member of C. So if I had, for example, another set in F that contained 1, 2, 3, 4, then so it contains each member of the chain, then F contains a maximal member. Essentially, that says that if you can encapsulate every single subset of sets in the chains with a single set, then that set contains a maximal member. It is quite a mouthful to talk about sets containing sets and whatnot. So essentially, if we give an example, so if I have a set containing a set of 1 and a set of 1 and 2 and a set of 1, 2, 3, and that is one chain. So this is a chain. And I have another set containing a set of 4. This shouldn't have comma. A 4, a 4 and 5, and 4, 5, 6. That is also a chain. And then if I have some set containing 1, 2, 3, 4, 5, 6, then this set can fit every member of every single chain. Right? This set contains every member of every single chain, and thus is a candidate to be maximal. So essentially, possibly maximal. And this is some f. So we could have 1, 2, 3, 4, 5, 6, 7, and then that with 7 would be the actual maximal element. But the existence of this set necessarily means that a maximal element exists. That is what this axiom essentially says. And so if you have a set, so if I write down another definition, so if I have that S is a subset of V, let S be a subset of V. A maximally linearly independent set, so a maximally, or not maximally, maximal, linearly independent set, a subset. Great. Subset. Subset of S is a member B of S that satisfies, so I just write it, linearly independent, of course, because that's a linearly independent subset. And if the only linearly independent subset of S that contains B is B itself. So if for every, let's call him C in S, sure, but it's supposed to be in S, where C is linearly independent, C is a proper subset of B. no, this is not quite correct, because I should because that includes B as well. Well, I can just write out with words then. So where that is B, that is linear band. The only member containing B. So that is what the maximal linearly independent subset of S is. And essentially, that essentially follows through to two more theorems. One of which if V is a vector space and S generates V, then if beta is a maximal linearly independent subset of S, then beta is a basis for V. And the second one being that if S is a linearly independent subset of a vector space V, then there exists a maximal linearly independent subset of V that contains S. And from the corollary of the last theorem, we can prove that every vector space has a basis. So that, I think we're essentially almost out of time, and I don't think I have time in the remaining 5 to 7 minutes to actually write out and prove the theorems. But so
yeah, I would say that now's probably a good time to just open the floor, and if there are any kind of final thoughts or questions, people can chime in.
yeah, essentially, I think my Discord didn't catch up with the Discord chat. But yeah, Kirby's Games asked, why wouldn't I be in C basis? That is because I can answer, but to clear up any confusion, if we have V, that is the vector space of complex numbers, over the field R, then we don't have a scalar that can give us I. So essentially, if we have the field to be complex numbers, then the scalar, then we can have 1 and have any scalar be a complex number that generates another complex number. And 1, because 1, anything times 1 is itself. So essentially, but if we have real numbers as our field, then only real numbers can be our scalars. So we need I as a base to scale with our scalars. Let's see. So as for the next question, if the dimensionality of a subspace is less than or equal to its host space, then the parent space has finite dimensionality. Doesn't it already mean the subspace can be infinite? Yeah, essentially, if a subspace is, so if a vector space is finite, or rather, no, wait, if it's less or equal to its host space. Yeah, okay, so if the host space is finite, has finite dimension, and the subspace has a dimension that is less than or equal to the dimension of the host space, then the subspace is in fact finite. Yes.
And I think
Right.
like
So
I think the point there for theorem 1.11 was actually to prove what we kind of intuitively think is true.
Yeah, essentially. If you have a subspace, you essentially want to prove that you can't have a subspace with a bigger dimension than the space is a subspace of.
Yeah.
Which makes sense because you don't introduce any new elements that would require a basis to be enlarged to be able to generate. So yeah, that is essentially what theorem 1.11 is. As for the chains, um, in the context of a fixed posit P, it makes sense to talk about the subchains and superchains of a given chain in C and P. Well, again, that would be more going into set theory, I believe, which isn't too useful to us learning linear algebra, right? Besides, I am not too well versed in set theory, so I'm not very confident in my ability to properly explain concepts further than what is required to understand Zorn's lemma.
And I think
So
for those
that
of you that want
includes,
to, for those of you that want to discuss chains a little bit more, again, it's a little bit out of my wheelhouse as well. But you're welcome to do that in the discussion part of the linear algebra group on Simple Server. I know that Stuki has a fair amount of knowledge, or at least more knowledge than I would have with regards to thinking about these things. So they might be a good individual to discuss this with if you're curious about talking
yep,
about this more.
most definitely. I find it funny how my writing became more and more bigger. I became just bigger and bigger as time went on.
It's a classic Excalibur problem, so don't worry.
Yeah, I imagine it to be that. Yeah. But
All right, I
still,
don't
the
know if anyone
important
else
thing is
has
that
any
everything
other.
is written.
Yeah, I don't see any other specific questions coming from Twitch or from Discord, so I'm happy to close off the lesson here if you are Glenade.
Yeah, sure. I feel like I don't want to go over the 2 hour limit to not keep people here unnecessarily. Basically what I wanted to introduce was at least some intuition for what the book calls the maximal principle, so that you can read forward and see the proof for every vector space containing a basis.
Right.
So, but apart from that, yeah, we are out of time, and while I would like to continue talking, I feel like it's not something that must be said in the lecture. So I feel like it's best to just close it off here and allow discussion to happen in the discussion channels.
Yeah, no, that sounds great. I'm gonna jump off of the Discord call just to finish off everything on Twitch, and I'll be back in a couple minutes if anyone wants to chat about anything else.
All right.
All right, friends, it is about that time in our lives. We are going to say goodbye to one another. Let me pop on some music here just as we're shutting down. You are more than welcome. Thank you, all of you, for coming and hanging out today. I will be back a little bit later today, so we are doing a Legend of Zelda run a little bit later. But we're going to close this off so that I can get this ported over to YouTube for the Linear Algebra Reading Group. So thanks again to all of you, and I'll see you a little bit later today.